Alright, so in this video I'm gonna be explaining another important article on model editing with the title of the paper is How do decisions emerge across layers in neural models? Interpretation with differentiable masking. So this paper in 2020. Attribution methods assess the contribution of the inputs to the model prediction. One way to do so is erasure. A subset of inputs is considered irrelevant if it can be removed without affecting the prediction. Though conceptually simple, eraser's objective is intractable and approximate search remains expensive with modern deep NLP models. Eraser is also susceptible to hindsight bias. The fact that an input can be dropped does not mean that the model knows it can be dropped. The resulting pruning is over-aggressive and does not reflect how the model arrives at the prediction. So to this end, they introduce differentiable masking, which learns to mask out subset of the input while maintaining differentiability. The decision to include or disregard an input token is made with a simple model based on intermediate hidden layers of the analyzed model. First, this makes the approach efficient because we predict rather than search. Second, as with probing classifiers, this reveals that the network knows at the corresponding layers. This lets us not only plot attribution heat maps, but also analyze how decisions are formed across network layers. You see, on the left, a model F with parameter theta prefers a prediction Y for input X. But on the right, our method uses a hypernetwork G. This hypernetwork G to update the parameters of F to theta prime such that f of x of theta prime prefers an alternative prediction without affecting the prediction of any other input. Our model edits the knowledge about x stored in the parameters of f. So we aim to understand how a trained model processes an input to produce an output. For an input X, we obtain the output Y of the model along the hidden states. We then probe the model using a shallow interpreter network, which takes hidden states to up to a certain layer L and outputs a binary mask indicating which input tokens are necessary and which can be disregarded. This reminds me, in the field of graphs, when you have graph, we have PageRank algorithm, shows the importance of each node. So we have personalized, local, PageRank, shows the importance of, and the solution, of course, is the steady state, that distribution, final distribution, that converges to a final distribution, which in probability we call it balance equation. But so the equivalent in this form, here we are not working about graphs, but you can think about it like that. Some tokens are more important. They are the heart, they are the center of the meaning. So in this way you can understand So we probe the model using a shallow interpreter which takes hidden states up to a certain layer and outputs a binary mask indicating which input tokens are necessary and which can be disregarded. Disregard because they don't have any big influence. If you do a sensitivity analysis, to assess whether the mask input is sufficient, we refeed the model with it and compute the output. As long as y hat approximates the original output y, well, we deem the inputs masked by z unnecessary. Masking, however, as a multiplication by 0, makes a strong assumption about the geometry of the feature space. In particular, it assumes that the 0 vector bears no information. Instead, we replace some of the inputs by a learned baseline vector b. This one is learned baseline vector. So the interpreter model consists of L+1 classifiers, the elf of which conditions on the stack of hidden states up to edge to predict binary votes to our keeping or masking input tokens. Each classifier is, of course, a kind of transformer, not graph transformer, a kind of transformer, because transformer, is a complete graph in which all tokens are related, anything can attend to any other thing. There is no substructure explicitly. So these are important attempts to make our algorithm more efficient. And you see this in model editing as well. So each classifier is a one hidden layer multi-layer perceptron. And so for a given depth, the interpreter decides to mask as soon as this holds for some k. And that is, in order to deem x sub I unnecessary, it is sufficient to do so based on any subset of hidden states up until h sub L. So there is no direct supervision to estimate parameters phi of the probe and the baseline b. Thus we borrow Eraser's objectives, namely we train the probe to mask out as many input tokens as possible, constrained to keeping this. And since often the output of f parameterizes a likelihood, and we formulate the constraint in terms of a divergence between the two functions' outputs. So a practical way to minimize the number of non-zero predicted by G is minimizing the L0 norm. So L0 loss is defined as a total number of positions that are not masked. And one here is the indicator function. We minimize L0 for all data points subject to a constraint that predictions from masked inputs have to be similar to the predictions of the original model. That's why we use this constraint. So, of course, this constraint, we use it in many papers on model editing, so maybe it's not new. But this idea is interesting, that to reveal which hidden states before information necessary for realizing the prediction, we modify the probe slightly. For a given depth, we use a mask to replace some of the states by a layer-specific baseline. So the resulting state is used to recompute subsequent states as well as the output, which we denote by y hat. So we do not aggregate votes with a product. Because of this probe, we want to discover whether hidden states are predictive of their own usefulness. For example, where did the practice, you see that this question answering token attribution, that B and C are misleading. not faithful, as they attribute the prediction mostly to the answer span itself. So our method D, this eraser, our method reveals that the model pays attention to other named entities and the predicate practice in both sentences. Predictions of the path-based methods are more spread out, and the exact search as well as approximate search leads to pathological attributions. And they did some experiments on sentiment classification. So their model is called DiffMask. You see that with a moving average baseline versus eraser, you see all metrics are computed at token level. And this is the sentiment classification, average number of layers that predict to keep input token.